Thanks for joining my talk. Thanks for having me here. Today I'm going to talk about my paper, which is Information on Fairness in Social Network, and appeared in STM 2020. This is a collaboration work with ML and AI team in LinkedIn. Moonghan and Hima were my collaborators from LinkedIn, and of course my advisor, Professor Sucheta Soundarajan. Because I cannot see chat box while presenting, I would appreciate if you ask your question in the end of my talk. Thank you. So you might have heard of algorithmic fairness. So actually algorithmic fairness recently has attracted lots of researchers. And so mainly they are interested in seeing fairness in algorithms related to machine learning. But what does it mean for an algorithm to be fair? So one possible definition is that different groups of people should be treated equally. And if they are not treated equally, there should be a reason for that. There should be a valid reason for that. And here by groups, I mean some protected attributes related to people in the network, like race, gender, or something like that. So this fairness in machine learning is growing, and there are even lots of conferences that are dedicated to this area, but there are very little work in network analysis, which is the area that our team in Syracuse University are interested in studying. So our goal in this work is to see whether structure of a network itself is fair or not. So we know that social networks are parts of people's lives today, and algorithms related to social networks have impact on people's lives. So for instance, suppose we have a company and we have a network of professional interaction between employees, and suppose all central nodes are occupied by white men, and minorities and women are in the fringes of this network. And suppose in this network there is an open position in middle or high level of the company, and people in the lower level of the company can apply for this position. If people like minority people that are in the fringes don't have access to this information, they won't apply for this job, so the network will even become more biased. And this has a bad impact on people's future. And in social networks, we also see some segregation, especially the segregation that exists in real worlds, like communication between people of the same race, gender, or something like that. So it is important for people to have access to information that spreads throughout the network. So our goal in this work is to characterize the information unfairness of the network. And by information unfairness, I mean fairness in accessing to information that spreads throughout the network. So if we consider two groups and information starts from one group, will it have equal access to members of both groups or not? After proposing a metric called information unfairness to characterize the unfairness of a network, we do a case study on computer science co-authorship networks to see whether these networks are fair or not. And then I will show how we can modify a network so that we could reduce the information unfairness that exists. So what I mean for the information flow in the network is that suppose we have these two networks. The network on the left is segregated. So we have a blue group on the right and a red group on the left. So if information starts from blue nodes, it can easily access other blue nodes. If information starts from red nodes, it can easily access other red nodes. And if information starts from any of blue or red nodes, it can easily access members of other groups as well through these green arrows. So we call this kind of network, although it is segregated, fair. And we mean fairness in information flow. On the other hand, if you look at this network in the right side of this slide, so we have this core periphery structure. So like the example that I mentioned earlier, like white male are in central positions of the network. So we could consider these blue nodes to be these executive positions of a company, and these red nodes are minorities and fringes, and maybe women and minorities that are on the fringes of the network. So in this kind of network, we have good flow of information between blue nodes. We have a decent amount of information flow between red and blue nodes through these green arrows. But because red nodes are isolated, they cannot reach each other easily. So if if a piece of information starts from a red node, it has hard time reaching other red nodes. So we call this kind of structure unfair. Now the question is how we can quantify the amount of information that starts from a node and reaches the other node. So there are lots of models for information flow or contagion process, like independent cascade model, linear threshold model, susceptible infected model, or something like that. But the problem with these models are that they are not stable and they require performing many simulations. And because we want to have a method that is tractable and we can compute it fast, so we try to estimate the flow of information using walks. So I show in a bit that length k-walk can kind of measure the flow of information between two nodes. So suppose we have this small network, and this network has two groups, black and white nodes. So if you look at the adjacency matrix of these nodes, this graph, so adjacency matrix has values 0 and 1. It is a binary matrix, and so the element ij is 1 if there is an edge between node I and node j. And it is easy to understand that this shows the number of walks of length span. I should mention here that walk is different from pass in a way that walks can be repeated. So between node 1 and 2, we have a walk of length 1, which is this edge, and we have a walk of length 3 that 1 goes to 2, 2 comes back to 1, and then 1 again goes to 2. So this is a walk of length 3 in this between these two nodes. But for pass, we have just one pass. Actually, one pass of length 1, and for length 3, we should consider this node. So edges cannot be repeated in the past. So the adjacency matrix shows the number of walks of length 1. And the interesting thing about walks is that if we compute the power m to the power of k matrix, it will give us the number of walks of length k. So with this in mind, we compute all the walks up to the length k, and we sum over them, which give us the number of walks of length up to k. So now we can use this information for measuring the spread of information. Suppose this guy, so suppose we'll start, this guy has a piece of information and wants to spread it to the network. And suppose the probability that this guy hear about this information, this piece of information is P. So what we do is that we multiply the adjacency matrix with that P value. And I should mention here that for simplicity, here we consider that the probability of flow between two nodes for every edge in the network is the same, and it is equal to P. But if we have information about differences in values, we can change this to PI, P1, P2, P3. So each pair of nodes can have their own probability, and we can still use this method. So when we have this matrix that tell us the probability that information starts from this node and goes to this node, we can again compute walks of up to length k, multiplied to the probabilities, and then compute the expected amount of information that flows between two nodes. Recall that I said that in walks, we can have repeated edges, and one might think that, okay, so if we have this length, if we consider walks of length 1, it's the amount of information that nodes receive is more than when we consider walks of length more than 1. And the good thing here is that because the p value is less than 1, when we multiply it to itself, this value becomes smaller and smaller. And so this gives us much more information that this length k walks. So actually we are kind of counting for that as well. So now that we know how we can measure measure the information flow, let's see how we can measure the information unfairness in the network. So suppose we have an attributed network with this is number of nodes, this is nodes, and this is edges, and we have adjacency matrix M. And by attribute, I mean that we have each node has a label that tells us its membership to a protected group like gender or race. Or in the previous example, the color associated with each node would give us the information about the attribute. And we have this integer k, which is the maximum length cascade considered. So, and the reason for considering this k is that all the information has some expiration date. So if there is an information available about an open position, that position might be filled after some time. So it is not realistic that we expect to hear information from people that are 10 hops away, and then we expect that information to still be valid. So we consider this integer k, and then this probability, which is a value between 0 and 1. And I mentioned that this can be different pair of nodes. And we have some, as input a distance function that tell us the distance between two distribution. And I will explain why we use that in a bit. And we can use different distance measure as well. So now that we know our input and we know how we can measure flow, let's see how we can compute unfairness. So suppose we have the same network that I showed before, and we have its adjacency matrix, and then we can construct the accessibility matrix. So the accessibility matrix is sum over P times M plus P squared, M squared, all the way to P to the power of K, M to the power of K. And actually, by this, each element in this matrix tell us the amount of flow that a node is expected to receive from the other node. And so this is the same as what I explained on how we measure the flow. So I should mention that because we are computing the number of walks and actually we are computing the amount of flow, it is not probability. So the value can be, the values can be greater than 1. And so in using this information, we don't consider the elements in the diagonal because we are not interested in the amount of information that people receive from themselves. So the information that will be echoed throughout the network and come back to that person. So with that in mind, we characterize flow between groups. So here we have 2 groups, white and black, and we have the label of each node. We have access to that. And we can have joint attribute as well. And joint is from information starts from white group going to white group, starting from white group going to black group, and information starting from black group going to black group. So that is joint groups, and then we compute all the elements in the matrix. So actually, we add all the elements in the matrix with this specification to a vector, which is our distribution vector. So here, for instance, for white to white, so this guy, so we don't consider this element because this is in the diagonal, but this guy gives information to this guy by 0.3, and this guy gives information to this one by 0.3. And here, I'm considering the network to be undirected and unweighted, but we can use this method for weighted and directed network as well. So for weighted, this adjacency matrix, instead of being binary, is weighted, has values has values that have that are between 0 and 1, and for directed one, so this matrix won't be symmetric. And here, by considering 2 groups, we should have 4 joint groups. So we will add one that starts from black nodes and goes to white nodes. But here, because it is undirected, the values will be the same, so I didn't repeat that. So now that we know we have these 3 distribution, and depending on the number of groups in our network, we will have more. Now we can compute information unfairness. So what we do is that we consider each pair of these joint distribution. So for instance, we consider this black, and then compute the distance to white-black distribution. We do it for all the pair of joint distributions. And there are different ways that we can compute distance between distribution. Here we simply use the distance between means. So a better approach will be Erasmus distance, which is more complicated. But for our case study, we realized that this distance between mean will give us the information that we want. But depending on the application, anyone can use any distance measure that is appropriate. So here, if you look at this black-black distribution and compare it to white-white distribution, so now we see the highest distance. So the distance is 0.57. Because these two distributions are very different, but if you look at these two distributions, they are very close to each other. So we consider the information unfairness to be the maximum value among all these distances. So here, the information unfairness of this network is 0.57. So if you look at these two networks, so they're kind of the same and similar to the network that I showed previously. So this network is segregated and this network has a core preferred structure. So what we do is that we compute the flow between red nodes, starting from red nodes, ending at red nodes, flow of information from blue to blue nodes, and flow of information from blue to red nodes, and compute the mean of this distribution and then their distance, which give us for this network 0.04, which is very low, which means good. The lower the information unfairness, the better the fairness of our network is. On the other hand, in this kind of network, so we see good flow between blue to blue nodes, 0.1. We don't see much flow starting from red nodes going to red nodes. So the information unfairness here is the maximum distance of these three pairs, which is 0.1, which shows this network on the right is much unfair than this network on the left. And we see that segregation doesn't mean that we have a network that is not fair, because we are considering fairness in information flow. So now that we know this information and we can compute it, we want to see how we can interpret that. So suppose we want to compare two networks of different sizes, and because a network is their size is different, so their fairness should be different. In order to compare these two kind of networks, we need to consider some kind of normalization, or even if we want to see why we are seeing this kind of information unfairness in the network. Is it due to the degree distribution, or does it have another reason? So in order to that, we can generate random graphs with the same property of interest, like the same density, the same degree distribution, or the same structure but different attributes, and see and compare the original network to these random networks. So actually computing lots of random networks is kind of expensive. So we kind of estimate the accessibility matrix of these random networks. And after estimating that, we could divide the accessibility matrix to this one and see how the unfairness changes. So suppose we want to normalize based on density. In order to have, so this is good when we want to compare two networks that one is dense and one is sparse. And we expect to see more unfairness in dense graph, but it doesn't mean that it is much unfair compared to the sparse one. We need to do this normalization. So what we do is that we estimate the adjacency matrix of these random graphs of the same density, where every elements have this value, which is 2 times number of edges divided by number of nodes squared. And then based on this adjacency matrix, we compute the accessibility matrix by multiplying this M to itself and multiply it to p-value as well. We can do the same thing for degree normalization. So in this case, each we are interested to see whether it is the degree that is causing this unfairness in the network. And in order to see that, we define a matrix, adjacency matrix M, that estimates the adjacency matrix of a network with the same degree distribution. And what we do is that for each element, we have a degree of, for each element in the matrix UV, which is node U to node V, we compute we multiply degree of node U to degree of node V and divide it by the number of nodes squared. And this is similar to the normalization used in famous modularity metric. So with that, we can normalize our matrix and interpret our results better. So when we started this work last year, so we were among the first groups that were considering fairness in in social network algorithms. And there wasn't any work that was measuring fairness in terms of information flow. There is this metric, this notion called Homophily, which measures the extent to which individuals associate with like-minded others, which is often measured by a sortativity coefficient in networks. So this is mainly used to see if a network is fair, if we don't want to consider the flow. And I will show here that if we, that this homophily cannot capture the information unfairness that we are interested to compute. So these two networks, so they have the same number of nodes and edges and the same number of nodes in each group. We have 4 intergroup connections and we have 20 intra-group connections. And the assortativity coefficient in these two networks are the same. So both these networks have the same homophily. They are both segregated. But the information fairness or the information unfairness in these two networks are different. Because if a piece of information starts from blue nodes, can easily reach red nodes in the left network, but in the right network, we have this red node that all the information should pass through this one. So it is harder for information to reach from blue nodes to red nodes. And the information unfairness of this one is much higher than this network. So actually, homophily cannot capture what we are interested in. So now that we know how we can compute information unfairness in the network, we did a case study on computer science co-authorship network because this field is of interest of many researchers, and they tried, and there's this big push to increase the representation of women and minorities in computer science and technology fields. But recently, especially in social science literature, they say that if we just consider numbers and we want to increase diversity based on numbers is not sufficient. So we need to consider their interaction as well. So what we did is we selected 5 subfields of computer science, database, data mining, graphics, parallel processing, and security. And we selected the top, we selected the papers that were published in the top conferences in each field between 2015 and 2019. And then computed the co-authorship network. So all these networks, these 5 networks, are not segregated, so their sortativity coefficient is very low. And in most of these networks, male are dominated. So in parallel processing network, 82% of nodes are male. The best one for female is data mining, which has almost 1/3 of the nodes to be from female group. I should mention here that we inferred gender from genderized library. Actually, we know that genderized library is not the best library that exists for inferring gender. So for my current work, that is the extension of this work to be appeared in journal, I compared different, we compared different libraries, and we substitute this library to gender API, which is more accurate. And besides, so this, the information that these libraries give us is based on probability. So when we infer the gender of a name, it gives us with probability, for instance, 90% this name is male, and with 10% this is female, something like that. So in our extension, we are considering that error into consideration as well, so that our results are more accurate. But for this version, we are using the genderized library, which is a good library and can give us a good measure of whether our network is fair or not. So this is the result of information on fairness of these 5 networks. When we varied p-values from 0.1 to all the way to 0.9, this is, we consider k-value to be 6. So the results show that none of these subfields are fair as we expected. But we see that, for instance, parallel is much more unfairness compared to other networks. And so for the extension of our work, we did more in-depth analysis of why this is happening. So, and the reason that we are seeing this kind of unfairness in parallel processing is that this network has a core peripheral structure. We have a large K-core or clique in this network that are filled by male. So because of that, we see much more unfairness compared to other methods, other fields. So here, so we were expecting to see that men always have the advantage. But when we analyzed our result, we realized that this is not the case. So as I mentioned before, in order to compare networks with different sizes, we need to do some normalization. So this result that you're seeing is not normalized. So please don't compare between columns, compare between rows. So for instance, in parallel network, the amount of information starting from male nodes, reaching male nodes is much higher than female to female. Because I mentioned we have this core peripheral structure here. But if you look at graphics and data mining, so the female-female distribution has a higher mean. So it means that female can access each other more easily than male. So the information unfairness in these 2 networks is not based on male-to-male distribution, and that is something interesting. So we did some normalization based on density and degree. So this is the result based on density normalization. This is the result based on degree normalization. So after degree normalization, we see that these results, the numbers get much smaller. So it means that much, but not all of unfairness comes from differences in degree. But still these parallel processing network has the highest unfairness among the rest of the networks. This is the result of normalized based on degree. So now we can compare between columns. So here, again, parallel processing, male to male has the highest value compared to female. But what is interesting here is that when we normalize by degree in security and database network, the female has the highest value. So it means that we have a bunch of high degree male nodes that if we normalize that, they are not of advantage anymore. So this information is good when companies want to do something to reduce their unfairness. So they can see that this unfairness is caused by a degree, and they will think of some extra activities to do to address that. So now that we know that this unfairness exists in the network, is it possible that we reduce this unfairness? So actually this part is a bit tricky because it is not easy to say that we can change the social network or professional interaction network, but maybe companies can add some key individuals to a mailing list, or maybe they can detect those people that are being discriminated, and maybe they make some introduction between specific employees. They make sure some employees attend special meetings or something like that. So suppose a company can do that. So it can, or a professional network, we can add a set of V edges so that the information unfairness is minimized or decreased. So the input is the same. So we have an attributed network with adjacency matrix M. We have this integer K value for the length cascade considered, and also we have this probability. And based on that, we want to propose a heuristic called MaxFair. But the problem here is that this problem is not submodular. So actually, suppose we have this network that has low information unfairness, a simple network with just 4 nodes, and suppose we add this edge. So there is no single edge here that we add, and unfairness decreases. Any edge that we add increases the information unfairness. Even now, this is the case. If we add this edge or any other edge, the information unfairness will increase. But at this point, when we add edges, we start our unfairness to be decreased from this step to this step. But here, after this step, again, if we add another edge, the unfairness will increase dramatically. And we cannot do anything about it. But when we add this edge, the information unfairness goes to 0. So this is just a small example, but we can see similar pattern in larger networks as well. So it is kind of hard to estimate which edges to be added to the network due to this property. The next thing that makes it hard is that we are not interested in increasing the flow between the network, like something that eigenvector centrality considers, detects the nodes that can spread the information most to the network. Instead, we are interested in increasing the flow of information between a specific group and making sure that it is not increasing to other groups, other pair of groups as well. So that makes it even harder. With that in mind, we did some heuristic, and what we did, so the idea, I won't go through the details, but the idea is that we, based on this accessibility matrix that we have, if we multiply it to the class of the attribute, a matrix that shows off the a membership to the attribute of interest, we can somehow estimate the centrality of each node based on the attribute of interest. So for each node, for each pair of nodes, for each node, we know that then we compute a number that tells us the centrality of node with respect to the group that it wants to spread the information. And then based on that and looking at which pair of groups have the lowest unfairness, have the lowest fairness, then we can detect those edges that adding them to the network will increase fairness. We do this in B iterations, and at each iteration we add one edge, but it is possible to make some efficiency improvements here. And so we can compute, we can add a bunch of edges and then recompute the information on fairness. And that will make it a bit faster. And in our current work, which is the extension of this work, we are making this MaxFair algorithm more efficient and more accurate. So for measuring this MaxFair, in addition to DBLP co-authorship network, we considered email enron network and also Norwegian interlocking directors as well. And so obviously there is no other method that we can use to compare our algorithm with, because there is no other method that are trying to decrease unfairness based on information flow. So we considered 4 baseline methods. One is based on degree. Two of them actually is based on degree. So we consider centrality based on degree. Again, I don't want to go through details of that, so that we could have some time in the end for question. We also considered a random network and random method, and also a method based on eigenvector centrality. And here is the comparison. So we have 1% of 1% budget. So we see how many edges exist in the network, and we add 1% of those edges into the network. And here is the result: the reduction in information unfairness in these 5 DBLP network, Norway and Enron. The black bar is the result of MaxFair, and the other bars are for our baseline techniques. As you see, in all but one data set, MaxFair performed better. And the good thing is, even when we change the network just by 1%, we see these increases in fairness by even 80%. And that is really a good thing. So the main takeaways of our work is that we proposed a novel information unfairness metric that measures whether information flows fairly to all groups in a network. We did a case study on computer science co-authorship networks, and we saw that none of the networks are fair, but there are different reasons why they are unfair. Sometimes male have the advantage, sometimes female. And the good news is it is possible to reduce information unfairness dramatically, even with the slight changes in the network. So currently, as I mentioned before, I'm working on the extension of this work, and I hope it will appear in journal soon. And we are looking at the structural properties that are causing this unfairness. We also accounted for the error that will cause by inferring gender. And my other work is on considering a professional interaction network of a company and see if we have a partially filled network, can we assign candidates to unassigned positions so that we can minimize information unfairness? And this information is good if companies want to assess whether their hiring or assignment practices are fair, and if not, whether they can kind of improve that. Thanks a lot for listening to my talk. If you are more interested, you can look at my paper. And if you have any question, I will be happy to answer. Thank you.